Our next speaker is Shri Dhruv Mohan, Director, RT Vision Technologies Private Limited. Shri Mohan studied electronics and electrical engineering from Manipal Institute of Technology. Mr. Mohan has designed cutting-edge AI systems for automatic traffic classification and violation detection, and developed an automatic number plate reader with a 97% accuracy. He has published several international research papers with the Spectrum Lab at IISc Bangalore, advancing the identification of retinal pathology. He applied the same concepts to temporarily track facial pathologies and recommend treatment vectors. Let's all put our hands together and welcome Shri Dhruv Mohan for his presentation.
A very good afternoon, everyone. And today I'll be talking about a product that we've been developing at RT Vision for just about 4.5 years. As the speaker very rightly, before me very rightly said, you need to do things about 3 times to get it right. And we're right now on our 3rd iteration of an automated wheel profile measurement system that has been designed from scratch in India and manufactured for India. Now, just a brief purview. A profile is essentially the surface geometry that you get once you cut normally into the center axis of the wheel. And it gives you a lot of information about the health of the wheel, whether it needs to be condemned, whether there are some aberrations or not. And it's important for proper functioning of your rolling stock. And one of the common defects that are expected from a wheel profile measurement system have been shown over here. Now, the way to do it, the standard practice right now is to use manual tools. And their least count is about 1 mm, which isn't pretty high. They're prone to human error. And it's a cumbersome and time-taking process. When I did it myself, it took me 3 hours just to do 16 wheels, which is really not sustainable for the volume of wheels that we have. And so we decided to make an automatic system to detect the wheel profile and deliver all of these faults automatically as soon as possible. Now, we've designed a system that does online in-track measurement of wheel profiles. We immediately report the wear characteristics and dimensions. At a speed of 50 kilometers per hour, we've measured an accuracy of about 300 microns. Because of the volume of data that we've collected, we can do predictive analysis and schedule maintenance as well. All standard parameters and more are reported by the system. You have a web-based database and can visualize this on your phone and on any internet-connected platform. Our optical system is IP68 rated, which means that if the system is submerged indefinitely, it'll work after the water is passed away. And we have planned for minimal maintenance, which essentially means that the system needs to be calibrated just once a year, and that's a 30-minute process. So once it's been installed, every year, a 30-minute process, just to make sure that the system is functioning properly. I'll give you a brief video of how the system actually looks like. So this is essentially what it looks like in operation. As the train passes, our lasers and cameras flash and they detect and collect data. And subsequently, we'll be going over our major components. Now we have, this is an approximation of a model of an ideal site of a deployment of wheel profile. We have wayside equipment and trackside equipment, and we'll be talking about our wayside equipment first. Now, in the wayside equipment, we've got a control panel and a power panel. The idea or our philosophy is to give you the results as soon as possible. So all of the processing that's being done is done in the control panel through an embedded system and a Windows-based PC as well that marshals all of the data, collects all of the faults, and immediately sends an SMS or email or however so you want your notifications to reach you. It also marshals the data and sends it to our cloud-based system so that you can visualize this on your phone or on your laptop. Our power panel basically ensures that there's a battery backup of an hour, and we have a conditioned power supply. These are the same points that I mentioned earlier. Our control panel has an industrial PC for image processing, acquisition, for self-diagnostics. We have a modem for sending data and to our cloud system as well, surge protection to protect our system from EMI, EMC. Our power panel includes a UPS with a battery backup of an hour, and the major power components are our blowers from the purging system and our control panel. Now, it's a bi-directional system, which means that we've installed wake-up sensors on either side of our main optical components. And this lets us know when the train has entered our track circuit. It lets us know the speed of the train as well as the direction of the train. And another critical component is our central trigger system. We're using a Frusher RS110 sensor. And the idea behind using a very accurate central trigger sensor is to trigger our lasers and cameras at the same time for each and every wheel, regardless of their lateral movement, regardless of the shape or the diameter of the wheel, so that we can collect consistent data. Now, we've collected data of the wheels, but we need to associate them with their specific coaches. And for that, we have an interface for an RFID system as well. However, since RFID isn't that prevalent, we also have developed an OCR system. We use an OCR camera, which collects coach images, and we run our own OCR software, which then identifies the coach number and then tags that specific axle to that specific coach. So the idea is, by the end of the train incident, you want to know exactly which coach's axle's wheel has created an issue, has created a fault. And our trackside equipment, it looks like this. This has been installed for testing at an EMU shed. We have 4 bays, which contains about 8 cameras and 16 lasers. And we'll see the operation of this in the subsequent slides. Now, as Mr. Rupesh very clearly said, rightly said, we have peculiarities of our own in India, and a very challenging aspect for optical systems in India is dust and debris. In fact, in our testing, we've had oil splatters on the system as well. And to prevent any damage or any sort of dust or grime falling on our optical components, because if that happens, then your system is dead. You have to replace your optical components. We've designed a purge system which throws about 18 meters per second of air at a very high velocity and at a very high mass flow rate, and that prevents rain, oil, dust, or debris from entering the system. So I have a video of that. As you can see over here, this is a mock-up model, and I'll pour some water inside, and it's all going to get blown off. And this prevents anything from entering inside the system and really mucking up our optical systems. Now, when the system is not in operation, that is, a train is not present inside our track circuit, we have shutters which close, which open and close, and that prevents the system from any sort of physical damage. So when it's not in operation, our shutters are closed. And when we've detected a train, they open up, and our purge system activates. Now, the heart of our system is what we call a monoblock. It's a rugged, single piece of, heavy piece of aluminum which houses our cameras and lasers. We've designed it to withstand a shock of 50 Gs, and the cameras and lasers that have been attached to this system are IP68. We have a total of 8 monoblocks, which means about 8 cameras and 16 lasers. Our cameras have a resolution of 5 megapixels, and with our subpixel laser detection technology, we can get a spatial resolution of 10 microns. And we've developed our lasers in-house for Indian conditions. The optics that we've developed are temperature resistant, which means that the shape of the laser beam that we're throwing on the wheel, that doesn't change with respect to the temperature. And it has allowed us to test and deploy the system with ambient temperatures of minus 10 degrees to about 55 degrees Celsius without any failure of the optical components. And now we have doubled the number of lasers, and that's because our core tenet of our system is redundancy. In our practice, over the 4 years that we've developed this system, we've noticed that our lasers are usually the thing that fails first, and so we double the number of lasers, and our system accounts for any amount of laser failure, so that the rate at which you have to go to the site and replace components is minimal. Now, this is the raw data of a single wheel that you can see from the system. This has been captured from the site, and you have, on the right side, you have cameras on the thread side, images from the cameras on the thread side, and on the left side, you have images from cameras on the flange side. And now that you have the raw data, you still won't get the profile because you have to do the step called calibration. And calibration is a pretty involved process. We have a 6 degree of freedom robot which uses a micrometer precise calibration target, and it calibrates our system by taking about 2,000 images. So it calibrates our cameras and lasers by essentially orienting the plate in the field of view of our cameras and lasers about 2,000 times. And this enables us to have a very, very, very high accuracy. So in the lab, we get about sub 100 microns of accuracy. Now, this is done in the factory before the system is sent out. And once it's been installed, we also need to do a one-time global calibration on the field where we calibrate the entire system to finally get your profiles. And that's also, to make it as easy as possible, we've developed a robotic platform, essentially a Steward platform, with 4 separate calibration targets to calibrate our cameras or monoblocks together. And an operation of that looks like this. So again, the principle is the same. It shows the calibration targets to all 4 monoblocks per side about 200 times, and we get a lot of data and volume, and that helps us account for a lot of aberrations that we've seen in the field, which is lateral motion. We have accounted for lateral motion of about 2 to 3 inches plus minus on either side, and it also lets us service wheels from a diameter of 700 mm to 1200 mm. A profile looks like this. You have around 4,000 points completely, and that lets us not only give you all of the standard measurements that you want from a wheel profile measurement system, but any other unique fault that you want to detect. Since we have a tremendous amount of data, we can simply code that into the system and detect it. So sharp flange or anything else that cannot be measured very easily with normal standard available tools are measurable by this system. All right, now I have the profile. I can't use the manual tools which are currently used because their least count is higher than the least count of my system. This system has a least count of about 100 microns, whereas, like I said, manual tools have 10 times that, which a least count of 1 mm. So we need to validate our system, and the way we do this is once a train has passed over our system, we have the profile that has been generated dynamically by the system. Once it's in the yard or it's stationary, we take a standard 3D scanner. This one is a go-getter from LMI. It has an accuracy of 40 microns, and we scan the wheel completely. And we generate a profile in static conditions. After that, we sort of overlap the profiles that we've generated dynamically and statically. And as we can see over here, the profiles completely overlap. And we do that for as many wheels as we can, honestly. Since we generate our errors on the site itself, we have a robust software stack, which essentially consists of a grabber, which grabs the images from our cameras, a labeler, which labels the specific images of the wheel to their specific coach number, a logger, which detects which records any aberrations in the operation of the system, and a processing engine, which processes the images, gets your 3D coordinates, and finally gets your profile. We have a database, like we said. There's a cloud database which is interfaced by an application that can be done on your phone or laptop. I'll conclude in a bit. And so for high redundancy and high availability, we use this thing called logical replication. So each and every wayside system has a small inbuilt local database in itself, and using logical replication, even if I don't have connectivity to my cloud system, as soon as I get it back, the system syncs and you start getting data available on your cloud. A quick overview of this GUI screens are over here. You can search over a period of time about the number of incidents that have happened, warnings that have happened, the status of the system, and you can have a look at individual trains. You can set the parameter levels over here and get a trend analysis of how the parameters are degrading per wheel of that specific wheel for every time it's come into our system or our loop again and again. And if you want a detailed analysis of the train, we have a visual representation of the train and the wheels that have created a warning or a fault are highlighted, and you can get that report in a PDF format or whatever format is applicable. Right, so to conclude, I'll just show you a video of the entire system. It's a rendering of the entire system in operation. So when the train enters, our train presence system sensors wake up the system, our purging system activates, shutters open up. And when the wheel is at the center of our system, our central trigger sensor activates the lasers and starts capturing data. Data is processed on the site itself so that we can give you errors as soon as possible. So it classifies the faults, tells you which exact coach is creating that specific fault, and wait for an acknowledgement from the user. All right, so we've worked hard and we've developed a platform in which we have a system in which we can do smart measurements, and wheel profile is just the beginning of our portfolio. We hope to work with our industry partners to expand this. Thank you so much.